Let's solve this quadratic type equation. When we solve trigonometric equations involving a quadratic type equation, we're going to use the same techniques that we would use for something like 2x squared minus 1 equal to 0. And for this problem, we could add 1, divide by 2, and then use the square root property. I'm going to attack this problem in the same fashion. So first I'm going to add 1 to both sides, and then divide by 2. And I got cosine squared of theta is 1/2. Now I'm going to use the square root property to say that cosine of theta is plus or minus the square root of 1/2. Now the square root of a fraction I can think of as the square root of the numerator over the square root of the denominator. So this is really just 1/√2. That is a cosine value that I know quite well. Cosine of theta equal to positive 1/√2. That happens twice on the circle at pi/4 and 7 pi/4. Cosine value of negative 1/√2 occurs twice on the circle at 3 pi/4 and 5 pi/4. So I have 4 solutions to this equation: pi/4, 3 pi/4, 5 pi/4, and 7 pi/4. What happens if we remove the restriction? Well, there are a number of ways to express the infinite number of solutions to this equation when theta can range over all angles. One way to do it would be to simply write pi/4 plus 2 pi k, 3 pi/4 plus 2 pi k, and so on. And so we would add 2 pi k to all of these thetas, and of course, when we say k is any integer, then we end up saying that we can add or subtract any multiple of 2 pi from these values and get a solution to this equation. Right? So this is one way to express the solution with no restrictions. We can be a little bit more concise. Notice that all I am doing as I go around the circle is I'm just adding or subtracting pi/2 from the angle pi/4, right? If this is pi/4, 3 pi/4 is just this rotation plus pi/2, another pi/2, another pi/2, another pi/2, and so on. So one way to express all of these solutions in just one line would be to say pi/4 plus any multiple positive or negative of pi/2. And that would be a much more succinct way of stating the solutions to this equation when theta is unrestricted.